Usually, let's say we have the wind acting in X direction here and Y direction. First, we'll consider the, so generally we consider this as B, this as D. So this side will be windward, this will be leeward. So front side will be windward, the rear side will be leeward. Is it clear with this pen?
Yes, sir.
Yeah, okay. Then we all know that due to the boundary layer effect, the wind speed increases with the height. Generally, we get a shape like this, and we call this topographic multiplier. So you can have areas close to sea or open ground. Then you can have areas with some houses built up, or you can even have fairly larger buildings at closer spacing. Then generally we call this terrain 1, terrain 2, terrain 3. So you can get different terrains. Then which means at different heights we'll be able to get the velocity, and generally the wind pressure is given by Q, and it is generally given as Vs squared, and this K value is half the density of air. Density of air is 1.2 kilograms per meter cube. So you get 0.6, because rho is 1.2. So you get these values like that. And so K is 0.6, and Vs is equal to the multiplier, terrain multiplier. So there is the M terrain multiplied by the basic wind speed. So the basic wind speed is actually measured at a height of 10 meters above the ground level. So at a height 10 meters above the ground level, you get the basic wind speed. And so we call it the design wind speed as well. So in Sri Lankan conditions, we can use values like, there are different values emerging, and earlier we used to have values like 49 here, somewhere here something like 43, and rest of the country we used to have something like 33. But sometimes, you know, when you are dealing with tall buildings, generally, you know, there's a tendency to use a value like 38 meters per second. In a value like 38 meters per second in zone 3 as well. So we'll use this value of 38 meters per second in zone 3. So you can find the wind velocity at different heights using this equation. And when you know the wind pressure, we can find the wind force. So in the Australian code, the wind pressure actually varies with the velocity. So the wind pressure values vary over the height. On the windward side, and on the leeward side, you get something, a lot of turbulence. Because of this turbulence, you find that the wind pressure is almost constant on the leeward side. So you get a pressure like this, and this suction. And on the windward side, you get pressure. So this is what happened in the, this is how the wind loads are calculated in the Australian code. And here you get turbulence. And due to the turbulence, you will get, due to the turbulence, you will get now it's better, isn't it? So due to turbulence, you get a uniform suction on the leeward side and a variable pressure on the windward side. So that is the basic situation with respect to wind. And then we have to also look at what happens when a tall building is subjected to wind loads. So as the wind loads are acting, the building will deform like that. But in addition to this, in case of tall buildings, here they are relatively flexible. What happens is there will be a negative pressure zones occurring on the sides, and then in one moment this negative pressure will move that way, and as soon as it moves out, you will find that the negative pressure will start occurring in the other direction. So then the building will be dragged in that direction. So what you find is building could be dragged in two different directions as the wind moves around. So in addition to move in this way, the building will move this way as well. So we call this is the crosswind response. Whereas this will be the lawn wind. So you can get crosswind and a lawn wind response when the building is subjected to wind loads. So all the time building will be moving this way, building will be moving this way, which means that finally the building will be moving in an elliptical path like this due to the wind effects acting in a particular direction. So because of this movement, there can be accelerations, and we have to determine the magnitude of the likely magnitude of the accelerations as well. So today what you are going to see is how these accelerations can be determined. So in the Australian code, in addition to finding the acceleration, even for this wind loads, so wind force is given by a force coefficient, a windward coefficient, multiplied by Q Vs squared. So that's how, so this is the pressure multiplied by area. And here you get a windward coefficient. But in addition to all this, to take account of the dynamic behavior of buildings under wind conditions, there's an additional coefficient called C dynamic. There's an additional coefficient called C dynamic that can be taken into account when we calculate the wind effects. So if the building is having a natural period of vibration of, let's say, 0.3 seconds, then frequency will be 1 over natural period, or it will be 3.33. So if it is 0.5 seconds, it will be 2 hertz. If it is 1 second, the natural frequency will be 1. So the Australian code states is 1170 part 2 states that when the natural frequency greater than 1, you have to consider these dynamic effects. So these dynamic effects should be considered, and the wind force can be multiplied by the dynamic effects. So we'll first find how to determine these C dynamic effects, and then we'll find how to calculate the lawn wind acceleration, and then we'll find how to determine the cross wind acceleration. So these are things we are going to cover today. And first I'll show you this wind code. Screen. So this is the Australian code, and it has a lot of information. Have you used Australian code before, Janit? Janit,
Yes, sir.
have you used this particular code earlier?
No, sir.
No. Okay. But the concept is very similar, as I explained here, right? They allow for shielding, topography, and the terrain category. So I'll email this to you so that you can share with your batchmates.
Okay.
And you can see the pressure is given by half the density of air. That is, density of air is 1.2 kilograms per meter cube. So you get 0.6. V design theta squared. C figure, C dynamic. So says, consider this value when you are dealing with pressure. So the force, wind force is equal to pressure multiplied by area. So it's the same equations, very similar, like any other code. And then the one of the things about this Australian code is it allows you to determine the wind forces based on the direction, orientation as well. And the other thing is, they don't use a factor of safety for wind. What they do is, if you are designing for 50-year return period, you use 50. But when you want to design for ultimate limit state, rather than multiplying this particular wind force, the wind force corresponding to this velocity, by a factor of safety, they go for a higher return period. They go for a higher return period. So finally you will find the effect is more or less the same. So basically, when you are designing for ultimate limit state, you will design for higher wind speed, which means you will end up with a higher wind force. So under service conditions, you can get a lower wind speed. Under the ultimate conditions, you use a higher wind speed. So automatically you'll get a higher force. So when you take the ratio of this V1000 and V50, you will find that, it comes closer to something like, the net effect will be something like 1.5. So basically, even in Eurocode, the basic wind speed is basic wind forces are multiplied by 1.5. So we get load combinations like 1.35 dead load plus 1.5 times wind load. So the net effect is, when you use the partial factor of safety, you use the service wind and multiply it by the partial factor of safety. Whereas in the Australian method, they, rather than going for a partial factor of safety, they simply go for a higher velocity. Finally, the net effect is the same. So the difference between service and ultimate conditions would be more or less the same. And generally in Eurocode, the difference between ultimate and service conditions, wind, will be 1.5 factor that we use as the partial factor of safety. So then in the Australian code, you get multipliers for the wind direction. And because we don't have any records like this, in Sri Lankan conditions, we generally don't consider the wind direction when we are selecting the wind forces. But if all that data is available, you might be able to say in a particular direction, this is the wind speed, and in another direction, this is the wind speed for a particular town. But we don't go for that kind of accuracy. So basically, every direction we consider the same wind. And for different regions of Australia, then they have defined different wind velocities. And then they also allow you to consider the possibility for any amplification of wind when the wind is blowing uphill. And also they allow you to consider the shielding effect. If there are other buildings close by, they allow you to make some reduction in the wind loads. So then it actually allow for various other possibilities. And this is how we have considered the width of the building as B, depth of the building as D when the wind is acting in this direction. So it holds. And then you can see when you want to determine the wind acting on the building, we have to use a windward multiplier and a leeward multiplier. Windward multiplier for the external pressure is 0.8, and if the building is less than 25 meters of height, you can use a constant value, whereas when the height of the building is more than 25 meters, then we use this to relate the pressure to force, a factor of 0.8 for the windward surface. And on the leeward face, the leeward, you can see leeward face. On the leeward side, you can have different suction values depending on the ratios of the building. You can have different suction values. So I'll explain it a little later in little greater detail. And also the wind suction on side walls are also given. And then it goes on to various other parameters that may not be directly applicable to us. And these with parapet walls and all kinds of situations. And then we come to the tall buildings, and in this particular code, any building having a natural period of natural frequency of 1 Hertz, less than 1 Hertz is considered as a tall building or wind sensitive building. And when you have a 3-story building, then likely natural period of vibration will be about 0.3, which means natural frequency will be 3.33. If you have 5-story building, the natural period of vibration will be about 0.5 seconds, and that will end up with natural frequency of 2, because natural frequency is the reciprocal of natural period of vibration. So here you can see when the natural frequency is less than 1 Hertz, you have to, there are certain conditions under which the provisions of this code can be used. So basically what it says is this code is not applicable for freestanding towers and tall buildings with natural frequency less than 0.2. Natural frequency less than 0.2 means something like natural period of 5 seconds. So 105 is 0.2, and you will have a natural frequency, a natural period of about 5 seconds only for a building having about 40 stories. So you can see this Australian code can be used directly for up to about 45 story buildings. But if the building is taller than that and you cannot satisfy these conditions, then you may have to use wind tunnel testing to determine the wind loads acting on the structure. So if you cannot use this code, if you are outside the range of this code, then you may not have any other option other than using the wind tunnel testing to determine the wind loads acting on the structure. And then on the Alon wind response, the equation is given for C dynamic. There are a few factors to be calculated. And then it gives equations for crosswind response. And then there are a few equations to look for. And all those equations have been converted to graphical form as well. So here you get long equations, but all those equations have been converted to graphical format like this. So you can just get the values from charts rather than doing all the calculations. And then in the finally, there are quite a few appendices. And finally, it tells you how to calculate the peak Alon wind acceleration and also how to calculate the peak crosswind acceleration. So if you look at this code, you'll find that wind pressure is given by K times Vs squared, which is a usual equation that is used in almost all the wind codes. And then finally, it will allow you to calculate the wind induced acceleration in the building. So if you are designing a tall building, then it's useful to make this check, because if you find that the building is moving too much after the construction, then it will be difficult to correct it. So it's better to take all the precautions at the very early stage. So that is one of the advantages of using this Australian code, because it allows us to calculate the wind induced, or not calculate, I'll say estimate the wind induced acceleration of the building in two perpendicular directions. And when you check it, if you think the accelerations are too much, then you might have to change the structural form of the building. So with this background, we'll, gathering information from this particular code, I actually, prepared a small note so that, we can use that note for us to get a better idea of how all these calculations can be performed. So now I will have a look at a particular note. Right. So basically, if you want to determine the wind induced response of the building, first thing is, we have to see where we are. So that means, we have to say we are in terrain category 1, 2 or 3. Terrain category 1 is open ground. 2 is, with slight built up. Terrain category 3 is, some reasonable built up of buildings. And terrain category 4 is actually for city centers where you have a lot of tall buildings and shielding effects. So generally for isolated buildings, we can easily use terrain category 3. And when you consider the terrain category, you can see for a 30-meter tall building, that the terrain multiply is 1.09, and so basically we have to adjust the wind speed to suit that. And here you can see at a height of 10 meters in terrain category 2, the multiply is 1, which means the basic wind speed is here. And then what happens is, as the height of the building increases, and so as the terrain, you'll find that the obstructions to wind can actually reduce the wind speed to a certain extent. So what you do is, if you know the basic wind speed, which we consider as 38 meters per second in our case. So when you know the basic wind speed, you can multiply it by the terrain or height multiplier, so that we can obtain the design wind speed. So when you know the design wind speed, we can find the design pressure, and when you know the coefficient that can relate the pressure to the force, you can actually calculate the force as well. Because for our structural analysis, we need the force. So here you can see external pressure coefficient, CPE, for rectangular enclosed buildings. This building is enclosed. Yeah?
Sir, can you maximize the PDF? Because it's hard to see.
All right. Okay. Yes. Now better? How about now?
Yes, sir, now better.
Yeah, okay. So here you can see the external pressure coefficient of 0.8, and then on the windward side, on the leeward side, you get these values depending on DOB ratios. And so if you look at the lawn wind response, and first thing is to calculate this C dynamic value, and C dynamic is given by a particular equation like this. So we'll just get ourselves familiarized with these equations first, so that after that we'll be able to use it easily. So we'll first see what's meant by all these different parameters. And so when you are doing the calculations, H is the total height of the building. Z is measured in the vertical direction, and S is the level where you are calculating the effect of the actions. So that is S, and so when you are calculating the wind effects, generally S is taken as 0. When you are calculating the C dynamic value, the S is considered as 0, which means we are calculating with respect to the ground level. So Then h is the height of the building. Then you get so many factors that have been derived empirically using wind tunnel testing. So you get things like IH, GV, BS, and so many parameters. But we'll get a brief idea about what is meant by these parameters. And if you look at this equation, you can see this equation has two components. One is this BS component, the other one is SE component. So basically, when you have a tall building, it can respond to wind in two different ways. First one is, it will be a rigid body where the wind will come and hit the building, and that will give a static effect. That if the building is rigid, wind is coming and hitting the building, you get a static effect. The second component is, considering that building is not rigid, it is flexible. Because the building is flexible, building is going to move with the wind, and with that we are going to generate some kind of dynamic response. So the dynamic response is taken into account by using this second term. The static effect are considered by using the first component, and then they have been added. Square root is taken so that you will get the net effect. So that's how the wind effects are calculated. So this component refers to the static behavior, or the building is acting as a rigid body, and the wind is coming and hitting it. So this is what happens in a 2-story or 3-story building. Building doesn't move at all due to the wind, and so that is the static effect. And this is the dynamic effect where the building is actually moving with the wind. Then you get an additional effect due to this movement. Then to get the full effect, you have to actually add them up and then take the square root of it. So this factor responds to the static effects, and this factor and this factor, once combined, they refer to the dynamic effects. And in addition to that, in this particular equation, you get some meetup factor, and that is actually the damping effect. That is the damping effect. And so you have already learned certain amount of dynamics, and there's a parameter called critical damping. Critical damping means the damping is so high, that the vibration of the structure will come to stand still after one cycle. So that is the critical damping. And as a function of critical damping, these different damping values have been defined. So generally the damping available in the structure can be about 3% of damping, 3% of damping, 3% of critical damping at ultimate level state. But under service conditions, the structure is tracked to a lesser extent. So because of that reason, the damping is also low under under lower wind speeds. So when you are looking at serviceability conditions, we generally consider lower damping values, whereas when you are considering the ultimate effects, we consider higher damping values. So I'll show you how to use how to select the correct ones as well when you do the example. And in these equations, you get this IH value, and to determine the IH value, which depends on the terrain category and also the height, a table is given. So in addition to that, you get, so these C dynamic. So this is the C dynamic value. Then we can also calculate the acceleration in the along direction, and there's a long equation. So we'll see how this equation can be used to determine the acceleration in the x direction or the windward direction. And then there's another equation given to determine the acceleration on the crosswind direction. So with an example, we see how to make use of all these different equations, and then you will get all these charts to determine what we call CFS, and CFS appears in this particular equation. Here you can see CFS appears in that particular equation. So we'll first have a brief look at the example, and then take a short break, and then discuss the example. So example is for a 33-story building having a floor-to-floor height of 3.3 meters, where the length of the building is 36 meters, the width of the building is 34 meters, 34.5 meters. And the natural period of vibrations also are given. And we have been asked to determine the C dynamic value for a wind speed of 38 meters per second. And also we have to see the acceleration of the building. And generally, when you look at the acceleration of the building, we do not design for a very long return period. Generally, under acceleration conditions, we consider a return period of like what you call 1 to 2 year return period, because you know, just because you felt little acceleration in a windy day, it's not going to do much harm unless the acceleration is too high. So because of that, we do not check the accelerations for very high wind speeds. We generally check the accelerations for slightly lower wind speeds that can occur with a return period of about 1 to 2 years. Whereas when you are designing, we design for a longer return period. So generally we use 50-year return period when you are designing for ultimate limit state. Whereas when you are designing for service conditions, you can actually do the designs for a lower return period. So that's why you can see when the building is designed, it will be designed for a 38 meters per second. But when the wind-induced accelerations are checked, it can be designed for a lower wind speed like 25 meters per second. Can you understand this? Under ultimate conditions, we have a longer return period, whereas when you are checking for wind-induced accelerations, which is a serviceability condition, we use lower return period. And with that, you will see that we have to use two different wind speeds when you are calculating the response of the building. So this example has captured that particular aspect. So that's why you get a wind speed of 25 meters per second and 38 meters per second in this particular example. 38 meters per second is used to determine any value relevant to the ultimate strength, whereas a low wind speed of 25 meters per second can be used when you want to determine the wind induced accelerations. So is that clear? So I don't expect you to understand everything because we have not used any of these equations yet. But what I like you to understand is the basic background. So basic background is, all these equations are based on a lot of wind tunnel tests that have been carried out. And so these are all empirical formulae. So we have to actually follow a method rather than trying to understand every bit of it. So some of these can be based on various parametric studies and so on. So with that, shall we stop for 10 minutes and then start again?